All right. So, welcome. Greetings, YouTube. Beautiful Mind here. We are taking some time to, this is going to be the next installment for our Calculus for Business. So, we're continuing with Chapter 1 on differentiation, and this is Section 1.2 Algebraic Limits and Continuity. A couple of objectives here are to develop and use the limit principles to calculate limits and to determine whether a function is continuous at a point. So as a quick recap, I think last time we mentioned something about what we mean by a limit, and limits are really just concerned with when we're close to some specified x value, right? So as we get close on either the left or right side of this x value, we were concerned with how does the function behave. As we approach that number coming from the left, what is the y value getting closer and closer to? As we get closer to this x value coming from the right, what happens to the y value, right? So with limits last time, we said that as we get close to this x value coming from the left and coming from the right, as long as they're getting closer to the same number, then we say the limit exists and is equal to that number, right? So now in this section, we're going to take that notion of what we mean by a limit and extend it further to this concept of continuity. So some limit properties, okay? So we say that if the limit as x approaches some number of a function is equal to L, and the limit as x approaches some a of a second function is equal to another number, and c is any constant, then we have the following to be the case. The limit of a constant is the constant of a limit, right? So say the function is just some random number other than, I mean, it still works for 0, so c is just any constant, right? So say we consider a constant function, it's just going to be some flat horizontal line. As x approaches any specific number, then the y should approach that constant, right? Because constant, no matter what x you go to, the output is constant. It stays the same. It's going to be the same y value, right? So hopefully that wasn't too wordy, but the limit of a constant is the constant, right? So that's the first property we have. Okay. Second property, the limit of a power function is the limit of the base raised to that power, right? That is, for any positive integer n, right? This is some positive integer. The limit as x approaches a of some power function is going to be the same as the power of the limit, right? So it's almost as if we pass the limit into the power function. So the limit of the power is the power of the limit, essentially. The limit of a power function is the limit of the base raised to that power, right? Or in other words, the limit of the power is the power of the limit. And a simple way of conceptualizing, it's almost like you can pass the limit into the power function. I think that's a safe way to articulate that. Okay, similar here. So the limit of a root function, right? The limit of a root is the root of the limit. All right, so it's almost like you can pass the limit into the root. Okay, so the first property with L1, we had the limit of a constant is the constant. The second property, we have that the limit of a power is the power of the limit. So basically, you take the limit of that base raised to the power. Similar with root functions, because the root is still just another power. The limit of a root is going to be the root of the limit of that base or whatever. Okay. Assuming that the limit is greater than or equal to 0, in other words, non-negative when n is even, right? Because again, you can't take the even root of a negative number. Okay, so that's fine. I think this is okay. We're going to kind of keep moving forward. So then the third property, it says the limit of a sum or difference is the sum or difference of the limits, all right? So similar, again, we're not officially passing it through, but that's one way you can visualize it to keep it simple. So the limit of the sum is the sum of the limits, right? The limit of the difference is the difference of the limits, right? So you can essentially, it's almost like distributing. We're not really distributing, but you know, that's kind of okay to think about it that way in this context. Okay. The limit of a product is the product of the limit. So the limit of the product is the product of the limits. Okay. So it's almost like it's kind of like distributing, but you know, and it becomes natural. These notions become natural as we kind of move forward and we get more practice. The limit of a quotient is the quotient of the limit, provided that the bottom limit is not 0, right? Because we just don't want to divide by 0. The limit of a constant times a function is the constant times the limit, right? So here we have a constant times a function. So the limit of the constant times a function, it's almost like we're kind of like pulling that c out. It's going to be the constant times the limit. Okay. So that's another technique or property that we have at our disposal. So we have the following example. We're asked to use the limit properties to find this, right? So let's see what we can do. I'm going to go here. I think that's okay. I'm going to let that kind of be for now. Okay. So let me start with what we're given. We have that's way too thick. Give me just a moment. We're going to go here. So we have the limit as x approaches 4 of x squared minus 3x plus 7. Okay. So we want to find this limit. All right. So now one thing that we said was the limit of the product or the limit of the sum or difference is the sum or difference of the limit. So it's almost like we can pass the limit into the sum or difference, right? So this is going to be the same as the limit as x approaches 4 of x squared minus the limit as x approaches 4 of 3x plus the limit as x approaches 4 of 7, right? I just essentially passed the limit into the sum or difference. That's the idea. We also said the limit of the power is the power of the limit, right? So with the next one we can do, this is the first expression, we can rewrite that as the limit as x approaches 4 of x. I'm going to say quantity squared like this. Okay. What we can apply in that second expression, we said the limit of a constant times a function is going to be the constant times the limit. So we can essentially pull out that 3. So we can rewrite that second expression as -3 times the limit as x approaches 4 of x, like this, all right? And then the last one, we said the limit of a constant is the constant, right? So the limit as x approaches 4 of 7 is just going to remain 7. So that's just 7, all right? So we have that one simplified. So for the first expression, so you have the limit as x approaches 4. So if you were to consider y equals x, the closer that x gets to 4 is going to be the closer that y gets to 4. So then that first expression is going to be, trying to think what property was that. Anyway, as x goes to 4, y goes to 4. So then that's just going to be, that's going to be 4 squared minus 3 times 4 plus 7. All right, I think that should be okay. And then ultimately we get what? 16 minus 12 plus 7. 16 minus 12 is 4 plus 7 is 11. All right, so when we did this one, I think my assistant there is confirming what we did, right? So when we did it, we got a result of 11. Okay, she said that's right. Let me try moving this to the top. Maybe that'll be more amicable for me. Okay. So let's see what's next. So now we have a type version of what we just did that's been pre-worked out. We know that the limit as x approaches 4 is 4. That says, okay, so then by limit property 4, the limit as x approaches 4 of x squared, right, is going to be basically the power of the limit. So it's going to be that like that. So 16. I think we got that part, right? Moving forward, by limit property 6, the limit as x approaches 4 of -3 times x, so that's going to be the constant times the function. So that -3 we can essentially pull in front, and you see it here. And you get -12. I think we got that one as well. And then by limit property 1, the limit of a constant is the constant. So then when you put all those together, you get the same result that we got. Okay, hopefully that was okay. Let's try another one. So then we have theorems, limits of rational functions. So this is theorem 2. For any rational function f with a in the domain of f, then the limit as x approaches a of this rational function is going to be f of a. Let's look at that one more time. For any rational function f with a in the domain of f, the limit as x approaches a of f is just going to be basically you substitute in, right? That's essentially what we did in the last one. We had the limit as x approaches 4 of x. So our f of x was just x. We just essentially just plugged in there. We can't always, it's not always that straightforward, but that's always something to consider and you have at your disposal to try and see if it works, and then you kind of go from there. Okay. So let's look at this example. We're asked to find the limit as x approaches 0 of this expression, right? Okay, I'm going to apply the theorems that we just introduced and just kind of give it a go. So let me start with the original. First, we have the limit as x approaches 0 of the square root. We got x squared minus 3x plus 2. Okay, all of that's inside the radical, right? So then I think there was a property we said the limit of the radical is going to be the radical of the limit. So this should be the same as the square root of the limit as x approaches 0. Now we can say of x squared minus 3x plus 2, right? We essentially just pass the limit into the radical. Okay, provided some stipulations, but we're okay. So then this is a repeat of the previous example. I'm going to kind of go forward a little bit. So this is going to be the square root of the limit as x approaches 0 of x quantity squared. I'm just going to square it. Minus 3 times the limit as x approaches 0 of x. It's kind of a repeat of the previous. Plus the limit as x approaches 0 of 2. Of course, that's what happened. Anyway, I'm sorry. I was on hold and it took them for like ever to contact, and then by the time I realized, I forgot. I think they do that on purpose. Poor customer service. Anyway, it's okay. I'll call them back when I'm done here. Okay. So I think we got this down to the simplest form. So now we can essentially just substitute in, or plug in. Okay. So then the limit as x approaches 0 of x is going to be 0. So that first one's going to be what? 0 squared minus 3 times 0 plus 2. All right. So we essentially just replace the x's with zeros. So then this ultimately becomes just the square root of 2. Okay. Okay, let's see how we did. All right. So it says the theorem on limits of rational functions and limit property 2, so that we can substitute to find the limit. So they just kind of substituted right off the rip, right? I still kind of was breaking it down. They just substituted off the rip, which is fine. But notice we got to the same result. Okay. So we have a quick check. Find the following limits and note the limit property you use. I'm just going to find the limits. We already have a typed up version of this on the next couple of slides. So I'm just going to evaluate the limits. Honestly, for that first one, let's just plug in, right? Let's just do the same thing. So if we plug in 1, that's going to be what? 2 times 1 cubed plus 3 times 1 squared minus 6. That's going to be what? 2 plus 3 minus 6, which is negative 1. That's not a circle. Okay, so I'm just gonna leave that one as is. For the next one, it looks like we can plug in. I'm just gonna do that as well. So 4 squared is 16 times 2 is 32, plus 5 times 4 is 20, minus 1, over 12 minus 2. That's what, 52? So then it's 51 on top, divided by 10 is ultimately 5.1. Okay. And let's just do something similar here. I know I'm not stating the limit properties. I'm just doing it for the sake of time. So if we just substitute here, we got 1 plus, that's not a 1. 1 plus 3 times 2 squared, okay? Which is going to be the square root of what? 2 squared is 4, times 3 is 12, so that's 13. Let's just go with these, Okay, just for the sake of simplicity and time. Okay, so let's see it typed up. I mean, and you can kind of go through and verify the properties and things. This is what, slide 14. So the first one, you see what, -1? I think that's what we got. We got 5.1 in the square root of 13. So you see the 5.1 there. And you can verify with the limit properties, because that's kind of how we were doing it before. Just for the sake of time, I just kind of used them. And then I think the square root of 13. So I think we got all those results. We're just going to let those be. Okay. So in this example, we're asked to find this limit. Now notice, if you try to just plug in the -3, right? I think you get like 0 over 0, right? You get I think it's indeterminate form, or, you know, so basically you get a 0 in the denominator. So, but we can actually, so like if we were to look at this graph, because it's 0 over 0, right? That means that on the graph, at when as x approaches -3, at -3, when x is -3, there's going to be a hole in the graph, right? If we get a fixed number over 0, that usually appears in the form of an asymptote, like, you know, where the y goes to plus or minus infinity. But when you get 0 over 0, that usually appears as a hole in the graph, right? So if we were to look at this graph of x squared minus 9 over x plus 3, there should be a hole when x is -3. Like, it's not going to be defined when x is -3. But the y value should, coming from the left and coming from the right, should get close to a number. So with this one, what we're going to do, now we could make a table. Like, we could make a table where coming from the left of -3 and the right of -3, like we could do left of -3, we would do -3.5, -3.1, -3.01, -3.001. We can do those numbers and it'll approach something. And then coming from the right, we can do -2.5, -2.9, -2.99, -2.999, right? And get those points. But what I'm going to do in this case, I'm actually going to simplify this, right? We can actually simplify this. We have to be clear that it's not defined when x is equal to 3. So let me kind of just note that, hey, this is x cannot be equal to -3. But we can actually simplify it and talk about, well, how this function should behave as we get close to -3 coming from either direction. So instead of doing the table, I'm going to simplify. So let me start with the original. We have the limit as x approaches -3. On top, we got x squared minus 9. On bottom, we have this x plus 3. So what I'm going to do, hopefully I'm not jumping the gun. I might be jumping the gun. Maybe. Yeah, I'm just going to simplify. Again, you can make a table like we kind of did before, but I'm just not going to do that here. So this is going to be the same as the limit as x approaches -3. Now x squared minus 9 factors into x minus 3 times x plus 3, right? So that's something we should be comfortable with factoring at this point. Let me know if you need more practice and I can get something to you so we can be proficient there. And the denominator remains as x plus 3. Now we have some items that cancel. All right, we got x plus 3 on top, cancels the x plus 3 on bottom. This leaves us with the limit as x approaches -3 of x minus 3. Now with this simplified form, now we can plug in, and this will give us a sense of proximity, like what happens when we're close to -3. Okay, so now we can just plug in, and this is going to be -3 minus 3, which is ultimately -6. All right, so my claim is that as we get closer to -3, if you were to make a table, those numbers should get closer and closer to -6. Again, limit just tells us as we get closer. I'm not talking about at -3. I'm talking about close to -3. Right? Okay, let's see, how do we do? Okay. So note that the theorem limit of rational functions does not immediately apply because -3 is not in the domain, right? So, however, if we simplify first, the result can be evaluated at -3, which is what we did. So the x plus 3's cancel, and you see the -6. This means that the limit exists as x approaches -3, but the actual point from previous slide does not exist. It does not. Right? So as we get close to x equals -3, The limit exists because the left-hand limit equals the right-hand limit, but at 3 it's not defined, right? Okay. Hopefully that's okay. So this example, we are asked to find the limit as x approaches infinity, right? Okay, so now we're going to do the following for this. I have a technique and we're just going to do a similar line. I'm just going to kind of walk you through it. So first, I usually like to get a copy. So the limit is x approaches infinity. Now on top, we have x squared plus 4x minus 5. On bottom, we have 2x squared plus x plus 1, right? So now, I am going to factor out something where I'm just going to change the form of it, right? I'm not going to change the actual question itself. I'm just going to rewrite it in a form where we can evaluate this infinity. So since the highest power is x squared, I'm going to factor out an x squared from the numerator and the denominator and rewrite it and see what happens, right? So this is going to be the same as the limit as x approaches infinity. Now if we factor out x squared from the top and bottom, so I'm going to say x squared over x squared. So now on top, if we factor out x squared, that first term becomes 1. The second one becomes plus, 4 over x. And the last one becomes minus 5 over x squared. The denominator, if we factor out x squared, the first term becomes a 2. That's going to become plus 1 over x. And then plus 1 over x squared, right? And you can check by like multiplying back. If we were to distribute this x squared, that times that will give us our x squared. This times this will give us our 4x and our negative 5. X times that will give us 2x squared, our x, and that'll give us our 1, right? So if we were to, we can check, because if we were to multiply back, we would get back to the original, right? So that blue is just 1, so it kind of like quote unquote disappears. So now as we take the limit as x goes to infinity, for instance here, we have a fixed numerator. As that denominator right here, we have a fixed numerator. As the denominator gets bigger and bigger and bigger, this expression gets closer and closer to, can you see it? As that denominator gets bigger and bigger and bigger, this expression goes to 0. Again, with this next one, we have a fixed numerator. This expression essentially goes to 0, and it's the same thing. All of these kind of behave the same way. This goes to 0, this goes to 0, right? As x goes to infinity. Okay, and again, that blue part, this goes to 1, right? That's a 1. Okay, so then once we apply those notions, the only thing that's left over is a half. So then ultimately this equals 1/2. Okay, hopefully that's okay. Style like this. Okay, let's compare that to the prepared notes. So first we divide the numerator and the denominator by the highest power, right? I think they did the same step. And then the limit, okay, now I didn't write that last part, but that's essentially what we did. The limit as x goes to infinity. Again, the first part, the limit of a constant is the constant. The limit of a constant is a constant. And then as these terms all go to 0, because the numerators are fixed, the denominator expands indefinitely, so they tend to 0. As x goes to the far right, those tend to 0, so they just kind of go away. And you see we finish with the 1/2. This is fun stuff. I enjoy this. I don't know, it's just fun. I can't help it. I don't know what it is. It's just fun. It's like a puzzle, and I get paid to problem solve and figure out puzzles. It's just fun. It's just fun. Something similar here, right? Let's just do this something similar to what we just did. Let me start by getting a copy of the original. We have the limit as x tends to infinity. On top we have 2x cubed plus 5x squared plus 4x minus 1. On bottom we have 3x cubed plus 6x squared minus 7. Now I'm just going to do a similar technique. I'm going to come down this way this time. This is going to be the same as the limit as x tends to infinity. I'm going to factor out x cubed. That's the highest power. So I'm going to factor out x cubed. from the top and the bottom. On top, that's going to leave me with the 2 plus 5 over x plus 4 over x squared minus, I think it's 1 over x cubed. Okay, and now on bottom, that's going to give me 3 plus 6 over x minus 7 over x cubed. Okay. Okay. So now, if we take the limit as x tends to infinity, long story short, this tends to 1, this tends to 0, this tends to 0, this tends to 0, this tends to 0, and this tends to 0, right? And that leaves us with, looks like just 2/3. Okay. Now, I don't know that it's always like this. Whatever. Trying to get it out of the square mode, but it's okay. I'm just being nitpicky. So let's see, how do we do? And you see the 2/3. I think it's a similar argument. It's kind of like a repeat of what we just did. Okay, so we have some definitions here. So we say a function f is continuous at x equals a if f of a, now continuity, right? So we've been exploring these notions of a limit and what do we mean like when we're close to some x value on either side. So now we want to explore at that specific value, right? And that's where this notion of continuity comes in. We say a function is continuous at x equals a if the following. The function is defined at that x value, right? So if we plug it into the function is defined, the output at a exists, right? So first thing is that the function is defined at that specific x value. Second, we say the limit as x approaches a of the function exists. So the limit as x tends to a exists, right? So that's kind of repeating what we literally been talking about with the previous section up until this point. So this is a repeat of the previous, but what we're adding is that now the function at that point needs to exist, be defined at that point. So then the third notion is that the limit as x approaches a of the function is f of a, right? So again, with limit, we weren't concerned with at that point, like we were just concerned with close on either side, close to some point. So now for continuity, we're saying the function has to be defined at that point. The limit as x approaches that point has to exist, which means the left has to equal the right. And then thirdly, the limit has to equal the function value, because sometimes the function is defined at that point and the limit exists, but the limit sometimes is different than the function definition, right? And so that's not continuous. So the three stipulations: the function has to be defined at that point, the limit has to exist, and the limit has to equal the value of the function at that point. So once those three conditions are met, then we say a function is continuous over an interval from C to D if it's continuous at each point in that interval, right? So we need those three conditions to happen to talk about, I think this is continuity at a point, all right? And then to extend it further, we say a function is continuous over an interval if it's continuous at each point in the interval, right? So the above three notions are about continuity at a point, and then you extend those notions to talk about continuity over an interval, right? Basically, those three concepts apply to every point in some open interval, okay? In other words, you can't find points that refute those three conditions, okay? Okay, hopefully that wasn't too much. I'm trying to be as clear and I'm trying to make it as simple as I can. It's a lot initially, but I feel like once you kind of just keep trying and exposure and practice, it kind of sinks in. I definitely encourage you to go ahead and link up with the tutors if you haven't already. Also, I definitely encourage you to definitely like link up with your classmates, like at least 3 of your classmates. I encourage you all to work together. So let me go ahead and say this. I intend to say this in the orientation. I intend to make the orientation video after I do these lectures. But I went on and made all the homework and quizzes and exams for the semester all the way through the final. I went on to put everything on Pearson, right, which you access through Blackboard. But the only so right now you can access all of your homework and all of your quizzes for the semester. So if you want to go ahead and complete that stuff and finish, you can. That's my recommendation. You want to get out as far ahead as you can. So then that way, all you're going to be waiting for are my exams. Now I did schedule the exams to be released at a certain time. For instance, our exam one is going to be released as we go into week 6. For 7, like once it's released for 7 days, it's only a 7-day window where you can earn 100%, like anything over a 90%, right? Um, After the initial 7 days of the exam being released, is due like 7 days after I release it. But then you can still work on it past the due date. The hard deadline is that Sunday night at midnight going into Monday, going into the week of finals, right? So that's when everything is due. I'm not accepting anything past that point outside of the final exam because I'm going to have everything locked. And basically, once you take my final, I want the final to be the last thing that you do. I don't want you to finish the final and then still be having other work that you got to do for me. No, right? So that Sunday night going into that Monday of the week of finals, that's the hard deadline at midnight of all assignments. But I have some soft deadlines throughout the semester where, if you want over 90%, you got to submit it on time. If you submit anything late prior, it's late, but it's before the hard deadline, then it's only a 10% late penalty. So the highest you can earn at that point is a 90. So yeah, long story short, all your homework and quizzes, and even everything is available. Again, you can access your homework and quizzes right now. Just you got to be cognizant of the due dates for those assignments. Anything that's submitted late, and before the hard deadline is a 10% late penalty. So the highest you can earn is a 90. But if you want higher than a 90 on any assignment, you got to submit it on time. Another thing I wanted to kind of bring to your attention, I'm doing something a little bit different. Um, I assign prerequisites for every assignment outside of the final exam. So, like for instance, a prerequisite for the quizzes are earning at least a 50% on the associated homework assignments. Prerequisite for exams is earning at least a 50% on your quizzes, right? I don't really, and I tried to because we're going through so much information, I tried to be reasonable with the amount of work that I'm assigning. So I tried to dial back on the amount of work that I'm assigning because it's so much, right? I tried to do a reasonable amount. And again, and also I'm making your assignments available early because I want you to try to get out ahead. The sooner you can kind of get this stuff done as we approach midterms and other times, like critical times, at least my work can be done and you don't have to you can kind of schedule your stuff. Additionally, because we only have 2 exams, our exam 1 is different than the midterm for everybody else. I think that exam 2 kind of does clash with other exams, but at least one of the exams doesn't clash, right? There may be extra credit opportunities as well. I'm open to that. Anyway, I didn't mean to go off on that tangent, but I did want to just mention it and bring it to your attention. So we have this example. It says, is the function f given by this continuous at x equals 3? So in order for this to be continuous at x equals 3, we have to verify those 3 conditions. The first condition is that the function needs to be defined at f of 3. So 1 here. Let's consider, is the function defined at f of 3? Right? Okay. So then f of 3 in this case is what? 3 squared minus 5, which is 9 minus 5, which is 4. So that's a yes. Is it defined? Yes, it's defined. Let's do it like this. Yes, it's defined. Okay. So then the second condition is that the limit has to exist. The limit as x approaches 3 of f of x, does it exist? Okay. We can just apply those limit properties that we kind of talked about. So then this is going to be the limit as x approaches 3 of x squared minus 5. We can essentially just plug in because there's a property or a theorem that we just introduced. So this is going to be 9 squared, which is what, 81 minus 5, which is what, 76. So the limit as x approaches 3. So the y values, let me think about this. Did I do that right? Oh, I don't know why I plugged in 9. I knew something was off. I was like, wait a minute, that's not right. X approaches 3, right? I don't know why I'm thinking 9. Moving a little bit fast. So when you plug in 3, 3 squared is 9. 9 minus 5 is 4. All right, yeah, we go. That's better. So that checks. And then the third condition is that the limit as x approaches 3 of f of x needs to be equal to f of a, right? So basically the limit has to equal to the function value. And I think it works out in this case. And actually what I'm going to do is move this over just for space and continuity. Okay. So then the limit as x approaches 3 of f of x. So then basically, long story short, 4 equals 4. And we're good to go there. All right. So then we say, is this function continuous at x equals 3? We would say yes, because of these, it satisfies these 3 conditions. So we would say yes. Okay. All right. Let's try another one. I think this is a type version of what we just did. Okay. So first they show you that it's defined at that function value. So if you just plug it in, you get your 4. By the theorem on limits of rational functions, the limit as x approaches 3 of this function is also 4. Since the limit as x approaches 3 of the function is equal to the function evaluated at that point, then we say that f is continuous at x equals 3. Okay, not too shabby. On to the next one. So as a disclaimer, I generally don't look at these in advance, or I don't work them in advance, because I want you to kind of get a sense of how to like, if you just knew the concepts, how you should think about it, right? Like I do my best to not look them in advance and like, okay, let me see if I can work these out. Because if I look in advance, and sometimes it's like I'm leading the answer on. I don't really want to know the answer. I just want to get you to see how to think about these as best I can. Now, again, if you really want to get better about how to think about this stuff, my recommendation, definitely link up with the tutors and work together. There are some students that are going to get it a little bit better than others. You all working together actually serves everybody. It makes my job easier. Those that get it, it helps them to get it even better. That's honestly how I learned it when I was a student at Morehouse many moons ago. I may look young and act young, but you know I'm an ancient wise old sage for my mystics and anime fans and things of that nature. But but that's how I learned a lot of this stuff. I had a knack for it. It was fun. I figured out a way to get double paid to learn this information. Long story short, I was at Morehouse on scholarship and I did work study, and I intentionally chose work study where I can work on my homework. So I think I worked in, like, at that time it was Archer Hall. I guess it's still called Archer Hall. I'm not really sure, but I was I would check IDs. So I'll be sitting at a desk for hours on end. Anytime anybody came in the building, I checked their ID, and then when they left, which is like seconds later, I went back to doing my homework. So it was a no-brainer for me because because I'm getting paid to sit at this desk. That was the perfect time for me to do my homework. So when I got off work, I went and just did whatever I wanted to do. Hung out with people, did whatever. For the most part, that's how I got through most of undergrad. Um, yeah. And then, long story short, if you want to get good at something, it takes practice. Like if you think about gaming or sports or anything that you like to do, music, dance, whatever, you didn't just do it once and you got it. You do it over and over and over and over, right? So whatever it is that you want to be good at, it takes repetition. It takes repetition. The proof is in the pudding. Repetition is the key, right? So to get off of that horse and back on track, I started with some point and I kind of got sidetracked. I get sidetracked easy. I just be excited. Anyway, okay. So in this example, is the function g given by this continuous at x equals -2, right? So we have this piecewise function, and we see something happens to the left of -2 and something that happens to the right of -2, right? So in order for this to be continuous at x equals -2, we need to satisfy those three conditions. The first condition, we need to show that that it's defined. We need to evaluate g of -2, right? Okay. So g of -2, if we plug in -2, so when it's equal to -2, this says to use line 2. So then that's going to be -2 minus 1, which is -3. So the function is defined. So that first condition is satisfied. It exists. It's defined at -2. Second, we need to show that the limit exists. In order for the limit to exist, the left-hand limit has to equal the right-hand limit. Okay. So we want to consider the limit as x approaches -2. Now I'm going to break these apart into the left and the right, right? So first, let's consider the limit as x approaches -2. Let's consider it coming from the left. Okay. So coming from the left, that we're going to use that first line. This is g of x. Okay. So if we use that first line, that's going to be 1/2 times -2. I don't know, some of the stuff is in writing. Plus 3, all right? Let's have -1, so that's going to be what? 2. That result is 2, okay? But then, if we consider coming from the right, the limit as x approaches -2 coming from the right of g of x, this is going to be equal to, so that means we're going to use the second line. If we plug in -2, we're going to get -2 minus 1, which is -3, right? So notice that the left-hand limit is not equal to the right-hand limit. So what this means is that the limit as x approaches -2 of g of x does not exist. Does not exist. So then, is it continuous? We would say no, because the limit doesn't exist. We can stop there. We don't need to go any further, right? Because again, one of the stipulations of the limit has to exist. We showed that the limit does not exist, so it does not exist. I'm gonna just mark it with the red, right? That one failed. Okay. So let's compare this to the type portion. Is the function given by this continuous at -2? So you see where they defined it. They showed that it existed when x was equal to -2. To find the limit, we look at the left and right side limits. As we come from the left, we get 2. Let me make sure that I get that same thing. -2. Yeah. Coming from the left, we get the -2, right? But then coming from the right, we get -3, right? So since the limit as x approaches -2 from the left is not equal to the limit as x approaches -2 from the right, we see that the limit as x approaches -2 of g of x does not exist. Therefore, g is not continuous at x equals -2. Okay? Again, because this is a recording, you're always welcome to like pause, rewind, slow down. You can change the speed, you can slow it down, you can speed it up. You just have to do this on your own, at your own time, right? And I like it because it takes the pressure off of me to kind of fit it into a certain time limit. We'll do what we can during class. My intent is to use class time as like a study session. We can work through homework, ask questions, but this is the kind of stuff you should look in advance. And you should come to class with questions ready to go. Oftentimes students just are mute during class, which is okay. So I fill the dead air either with silence, or I might work on your homework for you. But everybody's going to have their own homework, the numbers, because it's the same questions, but the numbers it's basically an algorithm where the numbers change for each person. So you get your own unique question for the most part. Okay. Is g continuous at x equals 2? Let's do this one really quickly. All right. So first we need to consider we need to evaluate g of 2. Okay. So when g is 2, this says to use line 2 because that's when x is 2. So if we plug in 2, we get 2 times 2 plus 1, which is 5. Okay, so it is defined at 2. Second, we need to evaluate the limit as x approaches 2 of g of x. We need to see, does it exist or not. So we're going to consider the left and right hand limits. So first we're going to consider the limit coming from the left. Coming from the left of 2, that means we're going to use line 1. Okay? So the limit as x approaches 2 from the left is going to be 3 times 2 minus 5, 6 minus 5, which is 1. Right? Then, if we consider the limit as x approaches 2 coming from the right of g of x, this is going to be that one, 2 times 2 plus 1, 4 plus 1 is 5, right? So notice that the left-hand limit does not equal the right-hand limit. So then we could say that the limit as x approaches 2 of g of x does not exist. Does not exist, all right? So that one fails, so it's not continuous. Okay? Not continuous. Okay. Let's go on to the next one. Did we? Yeah, we finished that one. All right, let's just confirm we have a typed up version of what we just did. They evaluated at the point. They looked at the left-hand limit, right-hand limit. They got 1 and 5. We got 1 and 5, right? Since the limit as x approaches 2 from the left is not equal to the limit as x approaches 2 from the right, therefore this limit as x approaches 2 does not exist. So therefore g is not continuous at x equals 2. Okay, we're almost there. We have this function, is h continuous at x equals 3? Okay, repeat. So the first thing we need to do is we need to evaluate h of 3, all right? So if we're going to evaluate h of 3 right here, this says when x is 3, the answer is 7. So h of 3 is 7. So it is defined. It is defined at x equals 3. Next, we need to consider the limit. So the limit as x approaches 3 of h of x, right? The left hand equal to the right hand. Now I think we did one like this, similar, like if we just plug in 3, we get 0 over 0. So again, 0 over 0 generally appears as a hole in the graph, but usually the left hand limit and the right hand limit typically line up, right? So let's, so this is one where we can simplify. So this is going to be equal to the limit as x approaches 3. This is going to be the same as x minus 3 times x plus 3 over x minus 3. All right. So now we can simplify. These guys cancel. And we get, this is going to be the limit as x approaches 3 of x plus 3. And then from there we can plug in. We get 6. Okay. So we can say that the limit exists and is equal to 3. So that one checks out. But then the third stipulation, condition or whatever, is that the limit as x approaches 3 of h of x, and this is it needs to be equal to h of 3. But in our case, they're not equal, right? Here, let's do it this way. The limit ends up being 6. The question is that equal to h of 3, which is 7? We'll say no. So therefore, it's that's a no. So we say it's not continuous. Okay. So all three of those conditions have to be met in order for us to say that it's continuous at a point. Okay, quick check. I think we have a type version of what we just did. Okay. In order for this to be continuous, the limit as x approaches 3 of h of x equals. So let's start by finding the limit. So the limit as x approaches 3 of this function ends up being 6. But h of 3 is 7. So the limit is not equal to h of 3. Therefore, h is not continuous. All right? Same deal. Same thing as what we said. Okay? Quick check. Determine a c such that p is continuous at x equals 5. Okay, so what we're going to do is just work through those conditions again. If we want this to be continuous, the first thing that needs to happen is that p of 5 needs to be defined. Okay, it needs to be something. I'm going to leave that open for right now. I'm going to come back to that. I don't know what it needs to be equal to, but I know it needs to exist, right? So I'm going to come back to that. The second condition, or I guess it just needs to be equal to c. We'll say it needs to be equal to, not necessarily, I'm going to just leave it open. I'm going to just go with my first mind. Redo. Okay, now the second condition, the limit needs to exist, right? So the second thing we need is that the limit as x approaches 5 of p of x, it needs to exist. So because we're doing the not equal, it's kind of similar to what we had before with the simplification. This is going to be equal to the limit as x approaches 5. Now the top we can factor into x minus 5 times x plus 5 over x minus 5, and we can simplify. These guys are going to cancel. So then now when we plug in a 5, I think we get a result of 10. All right. So now in order for this to be continuous, the limit as x approaches 5 of p of x needs to equal to p of 5. So we need p of 5, we need that to equal 10. All right. So now if we let c, I'm going to do ours in purple. So for the third stipulation, because we need the limit as x approaches 5 of p of x to be equal to p of 5. Okay, so if we need this to be the case, for that limit, we got a result of 10. So we need that to be equal to 10, right? So then we're going to say let c equal 10 in order to make this continuous. So all I did there, I just went through the three conditions step by step. I just made sure that and we were given a little bit of freedom or wiggle room, right? So for the first one, well, we didn't have a result there, but then the second one, we found that the limit ended up being 10. So in order for this to be continuous at that point, the limit has to equal the value at that point. So in other words, we had to let c be 10 in order for it to be true. Okay, and I think that kind of brings this to an end, all right? Determine c. In order for b to be continuous, the limit has to equal the value at that point, which is c. So first we find the limit. The limit ended up being 10. So then therefore, in order for p to be continuous at 5, let c be 10. All right? Okay. That was pretty fun. So section summary. For a rational function for which a is in the domain, the limit as x approaches a can be found by direct evaluation of the function at a, right? In other words, we can just plug in with a lot of these, given some initial conditions. If direct evaluation leads to the indeterminate form, that's the word I was trying to remember earlier, indeterminate form of 0 over 0, the limit may still exist. Algebraic simplification and or a table and graph are used to find the limit, right? I think this section, we didn't use the table and graph, but we could have, right? But we were able to simplify, do some cancellations, and then evaluate, and we were able to keep moving forward. So these are just some suggestions or techniques. Informally, a function is continuous if its graph can be sketched without lifting the pencil off the paper, right? So in a graphical sense, we say a function is continuous. If you start at any point on the graph and you can trace the graph and get to every point without picking up your pencil, like there are no holes or gaps or breaks, then we say that the function is continuous, right? Formally, a function is continuous at x equals a if the function value, so the three stipulations, f has to exist at a, has to be defined at a. The limit as x approaches a exists, so we have to show that the limit exists. The function value and the limit are equal. So the value of the function at that point and the limit are equal. This can be summarized as the limit as x approaches a of f of x equals f of a. If any part of the continuity definition fails, then the function is discontinuous at that value. That was fun, all right? Hopefully. Okay, guys, so hopefully that's okay. I'm here for your support. Again, my intent is to use class time as a study session. We can go through homework. I can answer specific questions or concepts. My goal is to have these lectures available before class starts. I expect you to watch them before we meet, take notes as if you're in class, and then come to class with questions. Uh, Another thing is that I do intend to hold this session as an asynchronous session. And what that means is you don't necessarily have to attend the class. All I need from your end, all I need from you on your end is to check in and get your attendance credit each day. There are extra credit opportunities. I'm thinking in the form of, like, for instance, I need an intro and an outro, right? So, we can, like, if you want to make an intro and outro, and maybe we'll, like, you know, we can do like a talent show or a showcase, and like whoever gets like the highest, the most number of votes, whatever everybody agrees on is the best intro, they'll probably get, and like maybe no more than teams of 3 people, right? So whoever wins the tournament as far as the contest as far as the best intro, they can get that credit, and it'll be something. I'll try to make it worth your while. And I usually only do extra credit up until like a total of 10% of your overall grade. And I usually give it out in increments of 5. I might give the second and third runner-up groups extra credit as well. But that's one opportunity, maybe for the midterm, maybe for the closer towards the end of the semester, you can do an outro, right? So whatever, one team for the intro, one team for the outro. Um, if there are people or groups that would like to lead a session, like for instance, so instead of doing the intro and the outro, if you wanted to do like a YouTube short, like something that's either 15 seconds or 60 seconds, and you just do a quick presentation on something we talked about for that week. If you present it in class, like during class time, you and your group, whoever there's a point person and whoever you say you want to delegate points to, I would be open to some of those. Again, if we have more than one, I might make it a competition style, and I just try to get points spread around. But I want to encourage you all to be creative, and showcase and present and explain some concepts to us. Share, not only be creative, but make it relevant to what we're talking about. And see, can you take what we're talking about and can you relate it to something either in your everyday life or something that's going on in the world currently, right? But I wanted to be in the form of a YouTube short that you present during class. Probably for this class, probably on like Wednesdays, because I think we meet Monday and Wednesdays, right? I'm totally open to like extra credit in that form, and I'll keep track of it. I probably put it on. I'm still kind of going back and forth between Blackboard or Starfish for extra credit, but I'll keep log of it. I do have a way of keeping a record of it. I want to try Starfish, so it's not confusing students as far as the grade book. But I had to try some things out first there. Okay. So that's what I wanted to talk about for this week as far as section 1.1 and 1.2. We have our orientation, and I wish everyone the best, and let's look forward to a great semester and get her done. I'm available for support if you have questions. And on that note, we're going to end the session here. And from one beautiful mind to another, enjoy the rest of your day. Peace.